last time we did anti-differentiation, or to be more precise, the two types. We did indefinite and definite. Indefinite integral and definite integral. But what we haven't done yet is explain exactly what they mean. So we'll start off with a graph here. Notebook, come on. Okay, can you write this down first? Isn't it 93? Yeah. Come on, guys, hurry up. Okay, you have this drawn now? So, suppose we want to calculate this area here. What we could do is we could say it's roughly this rectangle here, and then roughly plus this triangle here on top. Now you can see it's not exact because the triangle here is a little bit bigger than the curve, but it's roughly going to be that. So if I call this x here, and I call this distance between them h, then this here will be x plus h. And what would be the height here? What would be this height here? Come on, what's this height here? What letter would represent this height? I realise it's Monday and it's 9 o'clock, but you're all awake, right? What letter represents this here? What? Guys, come on, wake up, wake up. What letter represents the height here? Yeah, come on. Y. And what does y equal? Chambers. Right, f of x. Right. And what about this one here? What's the height of this one? There we go. Now we're waking up. F of x plus h. Great. Okay. Right, so let's work out the area here. What would be the area of the yellow rectangle?
X plus h times f.
Nope. F of x times what? Not x plus h. Stop saying x plus h. H. I just want this, don't I? This is h, isn't it? Because this is x here, and this is x plus h. The width is h. Yes? Now, what about this triangle? It's half. Yeah, the base. Now, what's the height though? And don't say fx plus h. No. Fx plus h minus fx. This height here. Yes? Because this one here is fx, and this one here is fx plus h. So I just want this piece here. Yes? Okay. Come on, hurry up. Now, if you look here, you can see that, well, these two are the same at the front, so you can have a half hfx, this is hfx, yeah, plus a half hfx plus h. Is that right? Yeah, you can see this here. This one minus half here. Did you all write that down? Yeah. Okay. What's in common here? You can see a half and also h, so I'll take that out. Yeah? Now, remember, the derivative is roughly f x plus h minus f of x all over h. Do you remember this? Yes? Okay. So, if you remember that, you don't have to write it down, but you can write it down anyways. So, it's not quite the same, but we can kind of see that it's, it's not too different, right? Like, I mean, plus here, minus here, we're kind of missing a h in the bottom. But you look at this and you say, well, I could rewrite this, couldn't I? Maybe try to simplify this. So if you want, you can bring the h up here. So that's gone. And then I can bring the minus f of x to the left. Make it plus f of x equals that. And then I'll put that in there. Okay, so I get area equals a half h f of x plus h f derivative x plus f of x. Got this written down? I can go down a bit. Okay. Well, you can see here on the inside you get 2 f of x plus h f derivative x. So let's multiply in again. That times that will be h fx plus a half h squared f derivative x. Question? Yes? Is there a question? Okay, do you have this taken down? Now, nearly finished there. What type of number does h represent? Big number, small number, positive number, negative number? What do you think? Positive and small, yeah. So if h is small and... No, I haven't said this to you yet, but I'm sure you'll figure it out. Or did I? If h is small, then h squared, will it be smaller or bigger? Oh, no, it'll be smaller. Because if you think about 0.5, 0.5 squared is 0.25. So when you square a small number, it gets smaller. Okay? So if h is small, then h squared would be even smaller. So you can say, remember at the very beginning, whoops, I said that anyways this area is only approximately this. So it's fine if I want to drop this piece at the end. In other words, terms with h squared in it is so small that it's not so important, you can drop it. So I'm left with this. Now, getting to the end now, if I look at this, imagine I draw a tangent line here. What symbol do I use to represent the derivative? It's delta. Come on, please, you're not that tired. Delta y over delta x. And what do you think the delta x represents in this graph here? That's actually this piece here. And the delta y, the height here. So what letter represents delta x? Yeah, h, yeah. Very good. So we have area equals fx times delta x. Now, that is the area for a small little piece. Suppose I want the area of many pieces. What do you think I do? So like if I have a big shape and I want lots of little areas added together, what would I have to do? I'd have to add them all up, yeah? So what do you think I need to add to this here to finish it?
H.
This symbol. Just to add them all up, right? And believe it or not, although I first taught you integration as just the reverse process of the derivative, in fact, you can look at this and say, this kind of looks familiar to what you did last week. Like, what do we have at the end? Where's it gone? We have this delta x. What does that delta x look like? So let's say I start at x from A to B. What does this look like? What does this remind you of from last week? What does it look like? It looks like the integration, doesn't it? Like you have this delta x at the end, and then what do you have in front? This thing here. And what is this called? Lower limit, and this here, upper limit. And remember, when you're using the derived program, it even called it lower and upper limit as well. And in fact, it turns out that this is exactly the same as integration. So the result here, after all of that tiring work, is that integration in fact gives you the area. Problem? Beam? Problem? No. And that's the proof, yeah. But I should add a small little condition to this. This only works if f of x is positive.
I thought that's a problem.
No. If this was a problem in the exam, you might as well go home now. Do you need me to scroll up? Yeah. How far? Here? Further back? Yes? I'm looking at Brendan, he looks wrecked down there. Late night? Okay, scroll down. You have this? Got it? Okay, so let's have a look at some examples now. And yes, before anybody asks me, no, you don't need this proof for the exam. Yes, you could probably forget it and continue on in your lives happy, never remembering this. Yeah. Until if you do maths next year, engineering students. Okay. Medicine students, you won't see this again. Okay, let's have a look at an example here. So, I give you this curve. And I want the area between this curve and the x-axis. Okay, so if I draw this, what shape will it make? Concave or convex? Let's use our words. Concave. And how many people pictured a man inside of a cave when they said that? Yep, good, right. So it's working. So concave. Now, take out the calculator, mode 53. Give me the 2 points here. Yep. What is it?
4 and 3.
Okay. So I want this area here. Yes? Now, first question. Is the height of this positive or not? Is it positive height? Yes, it is. You can see it's positive height. So we can use our rule, no problem. And the rule says, or the formula says, the area will equal the antiderivative, the definite integral, from 3 to 4 minus x squared plus 7x minus 12 dx. Now you know how to do this. You did plenty of this last week. So starting off, what does the minus x squared become? Come on. No. Antiderivative? Nope. Not minus 2x. Minus x cubed over 3. The next one? Yeah, finally, minus 12x. And then you have 4 and 3 to put in. So, we'll put in the 4 first. 16 to 64 over 3. 16, 8, 56, minus 48. Minus 9. 18, are you breaking my train of thought? What? Which one? Here?
No.
Here?
Yeah.
Dx. Now where was I? That was minus 9 and then 9. Wait, what? 3 squared 9 times 7. 63 over 2. Minus 36. I'm not the one with the calculator, so you tell me what you got here. And it should be positive, of course, because it's area. Yeah.
1/6.
I think at the back I might have rounded it up to 0.17. It's 1/6, is it? So you can see, compared to the last two lessons, there's not really anything new here, except you now know the meaning of integration. It represents the area on the graph. For example, physics students, why do you think knowing the area on the graph would be important? For what type of problems? Where?
Graph, velocity and...
Yeah, those graphs. Time velocity graphs, remember? We calculate the area. Yes? Okay. Can I do another example? Do you have this written down? Yep, okay. Now this one's fine because the area is above. Yeah, so let's do one maybe where it's below. So I want the area between y equals x squared plus 18x plus 130 and x equals 8 and x equals 11. Somebody give me the two solutions here, please.
That's 130?
Yeah. Is it not right?
No.
What are the two answers?
There's
Error, like an I number?
yeah.
All right. Oh, well, it's possible that doesn't have roots. Yeah, that's fine. Yeah. So in this one here, it doesn't have roots. So I'm going to draw it looking something like this. It doesn't have roots. But I also tell you that x is 8 and x is 11, so we'll just use those. So this means I want this area.
Oh, so if you tell us that x is that and that, we don't have to look for that.
No, it could still have roots and you should still look for it. I'll do another one where it does have roots. So what would the area be here? X squared plus 18x plus 130 from 8 to 11 dx. Okay. I'll let you try this one for me. It's very similar to my first example. So I want everybody to do this now for me. 1, 1,
76.
yep, 117.6 the answer.
Can you go on to the last one before? 'Cause
Previous example.
I just want to, yeah. Okay.
Yeah? Okay. Let's have a look at another example. So, now let's look at one where it's negative. I want this area here. I cannot do this, not this. This is bad. No maths, no. Don't do this. Why is this wrong? What's the problem here? What did I say in my rule? You need fx to be positive. And what's the problem here? It's negative. Where is it negative? The second half, isn't it? Here to here is a problem. Here's fine, but here's a problem here. How do you fix that? In fact, it's very, very simple to fix. What you do is, you break this problem into two halves. The first one, 0 to pi, sine x dx. The second one, pi to 2 pi, sine x dx. And it's actually very, very, very simple to fix it. All you have to do is stick a minus in front of the broken part. And then that's it. So if you calculate this now, it'll give you the right answer.
They're both the same size.
Hmm?
We just need the first part.
Wouldn't you just need the first part?
That is the exact same size.
They're exactly the same, and it'd be twice this, yes. But this is probably the only time this happens. If this was a cubic, for example. Yeah, yeah. Okay, so here we get antiderivative of sine x minus cos x, very good. 0 to pi minus, and then again minus cos x,
Same x.
and then pi to 2 pi. Now these two minuses here make plus, but I won't, well, okay. I won't worry about that actually. So here is minus cos pi, minus minus cos 0, and here is minus, and then here is minus cos 2 pi, minus minus cos pi. Cos pi is minus 1, isn't it? So this would be minus minus 1. Isn't it cos pi is minus 1? Yes. And cos 0 is 1. Cos 2 pi is 1. And cos pi is minus 1. Yes. To how far here? The beginning?
Yes.
Sine x from 0 to 2 pi.
We were listening.
Alright. Two things can't be done at once, I understand.
So it's sine x 2 pi. Like how's the formula?
Go down?
No, wait.
Not this.
Yeah.
This bad. This here good. Go down, yep. Okay, can I do another example?
Why don't you just make the minus positive?
I wanted to mess with your heads here. I felt 3 minuses in a row would do that. Did it?
It's not, it's still minus.
Cosine pi is -1, isn't it? I sure hope so. I was after doing it now. Is cosine pi -1? Yes? Okay. Are you in radian mode, deal? Mm-hmm. Alright, can I do another example? Yep, okay. Hurry up. See, I don't have Ahmed here. He's my timekeeper.
No, I'm just gonna write that out.
Close enough. Another example now?
Yeah.
Okay, number 3 here. So, if you read this, I want the area between the x-axis, the line K, and the line L. So, let me draw the line L. Y equals 4x minus 8. And where does this cross the x-axis? The line L. Look at the line L in number 3. Where does it cross the x-axis?
Check for minus 8.
Yeah, where does it cross the x-axis? No? At x equal 2. And is it positive or negative slope? Positive. So going up or down? Up. Now the next line, the line x equals 3, is that horizontal or vertical? You had a 50-50 chance. It's vertical. So here is L, and then here is K, and then here is the x-axis. So you can see that I want this area here. And this is the line y equals 4x minus 8. Okay. 2? Look at the line L. When x is 2, that is when y is 0. That is where it crosses the x-axis. Yes? So, who can tell me the formula for area here? For this one. Come on. Antiderivative from to 3, yeah. 4x minus 8. Alright, so that would equal 2x squared minus 8x, 3 and 2, which would equal 18 minus 24, is that right? 3 squared 9, 9 times 2, 18. Yes, and then minus, put in the 2, that's 8 minus 16. Yeah, put in the 2. 2 squared 4 times 2 is 8. 8 minus 16 minus 8, okay. So that's minus 6, so 2 is the answer. Now, as you saw earlier, Hadil, there was another formula in this case because this is a special case. What type of shape is this? It's just tiredness, right?
It's a cave.
Now, the area of this triangle would be half the base. What's the base here? How big is the base? 1. And then multiply the height. How can I find the height here? I put 3 inside of which function? Well, the only one I have here. So 4 times 3? 12 minus 8? 4. A half times 1 times 4? Well, look at that. Yeah. No, Mohammed, not doing that again. I'll go up.
Yes.
This is a half the base by the height.
Yeah, it's just that we need to.
Yeah. So the height here is when x is 3. So that's 4 times 3 minus 8.
And why did you take 3 and not? Oh, it's 1.
Well, you don't need that. I'm just showing you that to help you see that it does actually represent the area.
Can't we use just that formula?
Well, it won't be like this in the exam. I only put this one here so you can see that it's the same, that it is the area, that it is 2.
Can you just go on?
Okay. Now I'll give you one to try here. Okay, let me just... Is that you, Muna? No? I heard it from this direction. Okay. You have a guilty look about you, Muna. Yeah. Okay. So what I want everybody to do now is get this area here. But in the exam, they wouldn't give you the graph. They would just say, here is this graph here, and find the area between this graph and the x-axis. So it's a lot like the sine x. So what's the first thing you think you have to do here? Find the x. What's that called? Find the roots. So you need to put this equal to 0 and solve, which you can do on your calculator, mode 54. Okay, so I want everybody to try this now for me. Give me the area here for this one. Isn't it mode 54?
One, three.
You try it there. I'll do it in a minute.
Well,
Get the area between this curve and the x-axis.
and if there's three answers for x,
There should be. Well, I made it so that there is 3 answers, yeah. Do a very quick sketch to help you with this. So you should all at this point have the 3 values for x, yep? What are the 3 values?
1, 3, and 2.
Yeah. So now you can calculate the area with those. Okay, let's have a look here. What the heck? There we go. You got 3 answers on your calculator. 1, 2, and 3. You can see some of it is negative, some of it is positive. So, firstly, we'll do the positive piece. No problem with that. That's just your regular, what's it going to be, 1 to 2 here. You can see there it is there. No problem with that. But this one here, we have to fix it. We stick a minus in front. So, again, 2 to 3. And then I'll do line 4 minus line 5. And that's what you should all have in your copybook. Except, of course, instead of fx, what do you have? You have the cubic here. Then use your rules. And you should have gotten a half. One last example, which I'll do here in Derive. It's exactly the same cubic as what you just did, except I now slice a piece off by using this line y equals x minus 1. Let me zoom in here. Center on cross. So now I want this area here. Who has any ideas how I could find this area here that I sliced off the cubic? It's a bit tricky, but I wonder if anybody has any ideas here for this.
Would be the derivative of the curve minus the derivative.
Yeah, well, not the derivative, but rather the antiderivative.
Sorry.
Look up here, look. I need everybody to look up, please. You see this cubic here? If we find the area underneath this cubic, and then we find the area underneath this line, and we subtract them, it gives us the piece in between. Now this is a basic idea when you think about it, because you learn about this in middle school. You know, when you have two shapes, and you want just a part of it, you would get the bigger shape, and then take away the area of the smaller shape. You all remember this from middle school? Yes? Good. So the same thing happens here. So in fact, all you have to do is calculate the big one minus the small one. There it is there. That's the cubic minus the line, and it makes another cubic. Why does it make another cubic? Well, because the x cubed from the first cubic doesn't go anywhere. So it's still a cubic. And then, just like before, but there's a slight problem now. I do start at 1, but where do I stop? What's the upper limit? Well, you can kind of see it here. What is it? It's roughly about 1.4. But how could you find out exactly what it is? Yeah, you need to solve where the cubic and the line